Okay, good day to all of you. So we are a third recorded lecture on the SSB part. So in this lecture we will touch upon the effect of frequency and phase error in the synchronous demodulation technique, which is carried out in SSB-SC as well as DSB-SC. What is the effect we will like to understand, and finally we will like to compare also. I am Professor Smith from Desai University. So as I said earlier also in my lecture, I said that prerequisite is that you should have basic knowledge of signal and system, Fourier series, Fourier transform and its properties. Okay, the learning objective of this recorded lecture is that after going through this, you should be able to understand what is the effect of frequency and phase error in synchronous demodulation for both the case of SSB-SC as well as DSB-SC. You should also be able to compare the performance of both with respect to the error, that what is the effect of error on both of them in both the cases, and then accordingly we will also discuss about the performance with respect to the bandwidth and all those things. After going through this lecture, you should also be able to build a block so that you can nullify the effect of frequency and phase error in synchronous demodulation of DSB-SC signal. Now, why I have not included the SSB-SC signal? Because we will show that whatever techniques are available for a DSB-SC signal, those techniques cannot be utilized for the SSB-SC signal. Okay, but there are certain techniques which are applicable to both of them. Okay, so let us proceed and get into the detail and get the notion of this. Now, see, in any suppressed carrier system, whether it is a DSB-SC or SSB-SC, okay, and if you are going for a synchronous demodulation, you should generate a local carrier at the receiver end. Now, ideally, whenever we do the analysis, we assume that local carrier ideally has to be in frequency as well as phase synchronization with the incoming carrier. But in real life, it may not happen. There may be a small, suppose carrier frequency is 1 megahertz at the transmitter side. You are modulating using 1 megahertz, but at the receiver side, it may be 1.001 megahertz. So it's only 0.0001 megahertz, but it will make a difference in the outcome. So if there is any problem in any of the frequency error or a phase error, then your detector output may be distorted. We don't know that it is going to be distorted or not in both the cases. So let us get into that. Fine. So synchronous modulator, when coming to mind, the ideal modulators looks like this, wherein this signal that is being received SSB or DSB, it is been passed through a product modulator which is cos omega ct. Whatever signal you get, that you pass it through a low pass filter with a bandwidth of 2 pi v, provided that m of t signal which is modulated is having a bandwidth of b hertz, that has been assumed. So you will get 0.5 m of t. This 0.5 is just because of the trigonometric identities, so it doesn't make much difference. So you can recover the signal m of t. Okay, this is using the ideal demodulator, but in the practical demodulators, not necessary. See, this is it's not necessary to be cos omega ct. Here I am reading omega c plus delta omega of t plus delta. This delta omega is nothing but the frequency error, which may be in terms of few hertz. It's not necessary to be in terms of kilohertz. Even as I said that if fc is 1 megahertz, okay, fine, but here it may be 1.001 megahertz, so it makes a difference. Okay, so what is the difference that we want to know? So just product modulator, you get some signal, pass it through low pass, we don't know what you are having over this, so we have to inquire this for both the case DSB-SC and SSB-SC. So first of all we will touch upon for the DSB-SC. Fine. So consider DSB-SC case where our received signal is m of t cos omega ct and our local carrier is in error. Okay, so I am taking not cos omega ct as a local carrier, I am taking it as cos omega c plus delta omega of all t plus delta, where this delta omega is nothing but the frequency error, which may be in terms of hertz, very few hertz also, and this delta is nothing but the phase error. Okay, fine. So phase synchronization is also important. So output of the DS, so what we'll do is this 2 is passed through a product, so output of DSP synchronous will be product of received signal and local carrier, and I am representing it as ED of t, that is detected. It's not an output, it's a detectors. Then I will pass it through a low pass filter. Okay, so I'm getting something like this m of t cos omega ct. So applying some trigonometry identities, okay, half multiply by half and multiply and divide by 2, I get this 0.5 m of t 2 cc. So I'm getting first term as cos delta omega t plus delta, another term is cos delta 2 omega c plus delta. Now this delta omega is very small frequency, this is 2 omega c, so this is centered at 2 omega c, and then I pass it through a low pass filter. So if I pass through the low pass filter, the second term is going to be compressed. So only thing suppressed. So the only thing that you will get is the first term, which is 0.5 of t cos delta omega t plus delta. Now see here, this is for the practical field, the practical modulator, wherein I have assumed that frequency error exists as well as the phase error exists. Now just to confirm that in the ideal case, if it would have been ideal case, then delta omega 0 and this delta 0, phase error 0 and frequency error 0. So if I substitute over here, cos 0 is nothing but 1. So I'll get 0.5 m of t. It was expected. Okay. So output will be 0.5 m of t if there is no error. But if there is an error, then what is the scenario? So what we will do, you will take two different cases. One is only frequency error exists and then only phase error exists. So let us take the case 1. Okay. Case 1 when delta omega is 0. What delta omega 0 means? Frequency error doesn't exist. That means only phase error exists. So the previous equation that we have come across, okay, that you can see that if you take delta omega 0, you will get only cos delta. Fine. So that is what we are getting over here. E of 0 t is 0.5 m of t cos delta. Now if you see this cos delta, this is not a function. Don't worry. This is not a function of t. Okay. This is just a constant. Fine. So some constant is multiplied. But as far as this delta is constant, so it is nothing but you can say maybe a net, because see, if delta is 0, then it is going to be 0.5 m of t. If delta is pi by 4, then it will be an attenuated version. But if delta is pi by 2, then the problem starts that it will become 0. So this is an attenuated. So as far as this delta is constant, so your output is not distorted. It's rather, if delta is constant, it is an attenuated version. So as long as delta is constant, output is proportional to m of t, and it is maximum at delta equal to 0 and minimum at delta equal to plus minus pi by 2. So it is nothing but you can say it is an attenuation, attenuated. So phase error causes attenuation of output signal. So it will not provide any distortion, but provided that delta is constant. Now if delta is not constant in such scenario, that is if the signal is going multipath, then what happens? The H and delta at each and every position, the attenuation at each and every time the attenuation changes. So it will result into multipath fading. So that there you have to be careful. Fine. For the DSB-SC, in short, if phase error exists, as far as that phase error is constant, then you need not to worry. It will just be an attenuation, not a distortion. And if there is an attenuation, then you can build up by using an amplifier after later on. So let's take the second case. The second case, if your phase error is 0, that means only frequency error exists. So it will cause delta omega t. Now here there is t. It's a function of t. Fine. So here you have to careful. So it is like some signal 0.5 m of t is multiplied with cos delta omega t. Meaning of that is your m of omega, which is spectrum associated at omega equal to 0, that may be shifted to plus minus delta omega. So two spectrum will overlap each other. The low frequency of part of plus delta omega with the high frequency of the minus delta omega, both will overlap each other, and that will result into something known as beating effect. So two different frequencies as if multiplied, something like that. So output in this case is definitely distorted, and if this is very small, the output signal is multiplied by low frequency, two low frequency sinusoids, and which will result into a effect known as beating effect, which is a very serious type of distortion. The spectrum of this I will show you later on, so it will be more clear to all of you. So in short, if there is a frequency error during the DSB-SC synchronous demodulation technique, it will result into the distortion of the signal. But if the phase error, then it is just resulting into the attenuation. Fine. So let us go to the SSB-SC demodulation. Now consider the SSB-SC case. Now here the received signal is m of t cos omega c t plus I have taken, it means LSB I have taken. This is in general true for the USB also. Fine. But for time being I am taking it as an LSB signal. This is nothing but the Hilbert transform m of t sin omega c t, and local carrier I am taking the same omega c plus delta omega t plus delta. Delta omega is the phase error and delta is the delta is the phase error and delta omega is the carrier frequency error. Fine. Local carrier frequency and phase error respectively. So output of the SSB will be the same product of received signal local, and it is been represented by ED of t. It's fine. So if I do this, but take the product of these two, so this will be product with cos, this will be product with sine. Okay, then I will pass through the low pass filter. So I know that with cos, if I do it, I will get delta or cos delta omega t plus delta somewhere, and another 2 omega c here also with sine delta omega t plus delta, and another is 2 omega. So 2 omega c t, two terms will be removed, which I have not included over here. That you mathematically you can write it in your book and do it. And when you pass it through a low pass filter, you will get only this two term, m of t cos delta omega t plus delta minus sine mh of t sine delta omega t plus delta. Now see closely here. Fine. So instead of just getting 0.5 m of t, I am getting this also, the product of that. Fine, m of t is been product with both of them. Sorry, not 0.5. I am getting 0.5 times m of t cos omega. So this is something some form of USB, you can say. Let us see into detail of that. And here see, let us confirm also whether it is correct or not. Suppose for the ideal case, delta omega is 0 and delta is 0. So if you substitute here, I will get cos 0 as 1 and sin 0 as 0. So this will go, fine, vanish. So I will get only 0.5 m of t. So for ideal demodulator is the same case, that is no error, then you can recover the signal very easily. Now let us take the two cases. Okay, that if delta omega is 0 means only phase error exists. So in the previous we have seen that delta omega 0, if I write, only sine and cos delta will remain. So I'll get 0.5 m of t cos delta minus mh of t sin delta. Now this in time domain you cannot understand very clearly. So what we will do is take the Fourier transform of this and try to understand. So if I take the Fourier transform of this, and it's E0 of omega, what I'll get is 0.5 m of omega cos delta minus mh of omega sin delta. Now what is this? What is mh of omega? mh of omega is nothing but minus j signum of omega. So for omega greater than 0, it is minus j here. Minus j mh of omega is minus j signum of omega into m of omega. So omega greater than 0, it is minus j, and for omega less than 0, it is plus j. So it will be, for omega greater than 0, it will be m of omega cos delta minus plus j sin delta, and for omega less than 0, it is m of omega cos delta minus m of omega sin delta. So m of omega I can take it common. So in one case omega greater than 0, it will be cos delta plus j sin delta, and for omega less than 0, it will be 0.5 m of omega into cos delta minus sin delta. So that will give me something like this. Okay, fine. So cos delta minus delta, I can take it as e raised to j delta and e raised to minus j delta. I think there is something wrong. By 2 has to be there, so 2 multiplies, so this will vanish. So m of omega e raised to j delta, m of to minus j delta. So what it means that for omega greater than 0, that there is a phase error. So delta phase distortion, it will result into phase error, will result into all the frequency component will be distorted by a phase of delta. So resulting into phase distortion in the detector output. Now as you know that our eyes cannot identify our ears cannot identify the phase distortion if it is present in your voice signal. Okay, it is not at all possible. Right? If there is an amplitude distortion, that's fine. If there is a phase distortion, it's not be able to identify. So there is no. So even though there is a distortion in SSB-SC signal due to the phase error, which was not there in the case of DSB-SC, but if you compare with reference to the voice signal, then it's not a problem even if phase distortion exists. So you can say that you can neglect the effect of phase error in both the cases. Now case 2, that is frequency error exists and phase error is 0. So in that case, it will result into 0.5 m of t cos delta omega t minus mh of t cos sin delta. So this, if you see closely, it is nothing but like a USB signal because of the negative sign. Okay, USB signal of m of t. That is what you are getting. Fine. Centered at what? Delta omega, which is very small. Okay, then you pass it through it means that it will not be a problem either, because it's only one of the band, upper side band of the signal. Fine. Okay, so it results into generating another SSB with carrier frequency delta omega, which is very small. Okay, so it means that each component of m of t is shifted by delta omega. So for voice it is tolerable, because you can use a filter and there is a gap there up to 300 Hz. Even if you compress, there is not a problem. Fine. Okay. So DSB-SC and SSB-SC, if you compare with reference to frequency and phase errors, and phase error in DSB-SC basically result into attenuation, provided that your phase error is constant. So it is not a form of a distortion. The phase error in the case of SSB-SC result into distortion, but if you comparing for the voice signal, then there is no issue. So it means that if you take for the if your m of t is a voice signal, then phase error doesn't make much difference for DSB-SC as well as SSB-SC. Now let us see for the frequency error. Frequency error in the case of DSB-SC, we have seen that it will shift the spectrum to plus minus delta omega, and which result into the beating effect. And in the SSB-SC, the frequency, it shifts each frequency components by delta omega. Right? It will be more clear if I show. See, suppose if your m of t is having the Fourier transform of m of omega in this shape without any loss of generality. Okay, with frequency error, if you are demodulating, you will get the same at centered at plus delta omega on minus delta omega. Now see here, if you see this, the low frequency sinusoid, two frequency component, low frequency sinusoids overlap with each other. So that will result into beating effect. Now if you go for the SSB-SC frequency error, if you do the demodulated, you got a USB centered at plus delta omega and minus delta omega. So there is a gap over here. So that's not going to be a great problem. Fine. Okay. So if you summarize, then it says that for SSB-SC, this frequency error or phase error is not a great problem if it's a voice signal. But for DSB-SC, definitely if there is a frequency error, it is resulting into beating effect. So you have to look for some circuit which can nullify this effect, remove this frequency error. So what is the solution to overcome the frequency error at receiver side? Okay, two solutions are such that which can be applied for all the cases. Fine, whether SSB-SC. In SSB-SC in general it is not required, but if you want, you can. Okay, the first case is that you use your quartz crystal, which are very stable, so there will be no frequency error. Fine. So two identical crystal you can cut to have the same frequency at transmitter and receiver. But if the problem is at high frequency, because if at very high frequency you want to have identical crystal, the crystal dimension are too small, so it's very difficult to have the match at the transmitter and the receiver. There may be small variations, there is a possibility. But if the carrier frequency is very high, then the another technique is that use this DSB or SSB, okay, and finally add a carrier or a pilot at very reduced level. Now these are just a pilot to have a synchronization, nothing else. Okay, not for an envelope detection or anything. So very small power level associated with it, along with sideband you send it. At the receiver side, what you do, you use a narrowband filter, okay, centered at carrier frequency, so that you can separate the pilot, okay, amplify it, and use that pilot signal to synchronize your local oscillator. Fine, so that is possible. Fine. Fine. Now this too you can use it for the SSB-SC as well as DSB-SC if you want. But in generally for the DSB-SC, the main two techniques they are used to nullify the effect of frequency error is, because phase error they are not concerned much, frequency error is signal squaring technique and Costas loop technique. So we'll touch upon these two and we will show that these two cannot be used for SSB-SC, not at all possible. Okay, and moreover we don't want also if it's a voice signal. Sorry. So let us see the signal squaring technique. So this is the block diagram of a signal squaring technique. What it says that m of t cos omega ct DSB-SC signal, okay, pass it through a squarer circuit. Output of that pass it through a band pass filter which is centered at 2 omega c, a very narrow band pass filter. Then output you pass it through a 2:1 frequency divider, so that you will get something like this, and use this, okay, and take the multiplier product and proceed. So if you see this signal, this is same cos omega ct we have generated, fine, from this itself, fine. Okay, there is no slightly phase shifting has to be provided to have the proper phase matching. Okay, that is needed. So let us understand mathematically how it happens and what it is. Fine. So squarer output, if you take here over this point, it will be m of t cos omega ct whole square, which is nothing but cos square omega ct. So 1 cos square omega ct is nothing but 1 plus cos 2 omega ct by 2. So you will get 0.5 m square of t plus 0.5 m square of t cos 2 omega ct. Then it is been passed through a band pass filter centered at 2 omega c. This is not a low pass, it's centered at 2 omega. So this will be compressed. Fine. And we are assuming that omega c is very much greater than b, where b we are assuming to be the bandwidth of the message signal m of t. So this will be compressed, only this much part will be left out, and this is assumed to be having a centered at here you can see that 2 omega c, but very narrow band. Okay, so very narrow band it is there. So it's not necessary that this complete part, some part of this will be available at E0 of t. So band pass filters, it suppress the first term, so complete does not pass since filter has a narrow band. Okay, we are assuming that the band, now if you see the bandwidth of this 0.5 m square of t cos 2 omega ct, okay, 0.5, it will be centered at 4b, it has to be centered, sorry, okay, centered at 2 omega c. The bandwidth will be 4b because it's a b is the bandwidth of m of t, fine. So m square will have 2b and it is been modulated by cos 2 omega ct, so it will be 2b plus 2b, that is 4b. Okay, fine. So now coming to back to this, fine. Now what is this? Let us understand. So this is nothing but, fine, your m square of t suppose is having, I am assuming that Fourier transform of a of omega. So definitely m square of t cos 2 omega ct Fourier transform, if you take, you will get 0.5 a of omega plus 2 omega c plus a of omega minus 2 omega. So this is centered at 2 omega c. So this is nothing but half a of omega minus 2 omega c, and this is half a plus 2 omega c, and the total bandwidth of this is going to be 4b. Fine. So if you take the filter here, which is centered at 2 omega c with a bandwidth of delta f, which is very much less than 4b, then filter will pass only this much part of the signal. Okay, so for mathematical analysis, I can see this is nothing but the width delta omega, this is the height, fine, keeping the area same, fine, and representing this as delta omega tends to 0, representing it as an impulse. So I can write this as delta omega into delta of omega minus 2 omega c, and this side delta omega into delta of omega plus 2 omega c. Fine. So if I take the product of these two, so this will take the value, okay, at omega equal to minus 2. So a of 0 I will get here. So 0.5 a of 0, delta of omega plus 2 and delta of omega minus. Hope it's clear to all of you. Okay, this is nothing but impulse function product I have taken. Fine. So it will be an impulse itself centered at 2 omega c, but the value will be taken, magnitude will be, not magnitude, area will be as if the value of this function to which it is multiplied at that point. Okay, so there is nothing but your E also. Now if you apply that, this delta omega is 2 pi delta f, giving 2 pi to this, delta f to is 2 pi delta of omega, this is nothing but cos 2. So if you take the inverse Fourier transform, you will get a of 0 delta of cos 2 omega ct. So this, at this point, you are getting a cos with a frequency, angular frequency of with a frequency of 2fc, not fc. We want fc, fine. Okay, and the product magnitude part, if you say, it is delta f, a constant, and a of 0, okay, which is also going to be a constant. Now what is this a of 0 that you can see? Okay, a of omega, we said that it's a Fourier transform of m square of t. So a of omega is nothing but integration minus infinite to plus infinite m square of t e raised to minus j omega t. So if you sub dt, so if you take omega equal to 0 on left hand side, right hand side, a of 0, so you will get integration minus infinite to it m square of t dt, because e raised to minus j omega, there 0, e raised to 0 is 1. So a of 0 is nothing but the energy of the message signal itself. So this will be em delta of cos 2 omega ct. Now if you see here, there is no plus delta or anything, no plus delta omega, so it is in phase sync with the income carrier. Only this frequency is twice, so pass it through a frequency divided 2:1, so you will get output k cos omega ct, which is in frequency and phase sync. Okay, take the product of this with m of t cos omega ct, so you will get the desired output and pass it through a low pass filter, so there will be no problem. Okay, fine. So that is what we say. Okay, now Costas loop. So here there is no issue. Now Costas loop technique, if you see, okay, m of t cos omega ct, fine. There is a local oscillator over here. Okay. Now see in this, the upper arm, this 2 times I have taken, 2 times just to mathematically, so you will get m of t output. Okay. So this is the local oscillator. Suppose it is generating 2 cos omega ct plus theta. Okay. So there is some phase problem. Fine. And this has been shaft pi by 2 shifter. So this is 2 sin omega ct. So upper arm output after the product, what you will get is nominal carrier frequencies. Carrier frequency, in this case, we have assumed that carrier frequency is known to us. That is omega c is properly known to us. Right. So local oscillator generate this carrier. Fine. So two low pass filters we are using over here, which will suppress the high frequency component. So if you take the product of this part, I will get one term as cos 2 omega ct plus theta, and another as cos theta. So low pass filter, I will get m of t cos theta, and in this side I will get m of t sin theta. Fine. So whatever output of these two is multiplied, so I will get half m square of t sin 2 theta. Fine. Now it is passed through a low pass filter narrow band, as I said previously, that if you use a narrow band filter, very narrow band filter, okay, you will get only not complete part of that you will get, only some part. So k sine 2 theta we are getting, where k value will be km em delta f. It is same as this calculation is same as the previous. Fine. So for small theta, if this theta is very small, in general it is going to be k sine 2 theta. I can write it as k 2k theta, so which is like a constant. So give it through a VCO, voltage controlled oscillator, okay, which is used to adjust the phase of this local oscillator. Now this local oscillator will adjust the phase, and once when we get theta equal to 0, when local oscillator is in exact sync with the incoming signal, then the output of this upper arm, this will be 0, this will be 0, this is m of t sine 0 is going to be 0 here. Fine. So this is m of t cos 0 is going to be 1. So output, upper arm output is nothing but your desired demodulated signal, and this will be locked. So this is some form of phase lock loop type. Fine. So this Costas loop, which is prepared for DSB-SC, so that you can remove the effect of the phase error. In this case, frequency error cannot be removed. Fine. So remark on SSB-SC, you can say that for the SSB-SC, you let us see whether it can be used or not. Signal squaring technique and Costas cannot be used for SSB. Why? Because see, in USB signal, suppose is given as m of t cos omega ct minus mh of t sin omega ct. So that I can write in terms of envelope, e of t cos omega ct plus e of t is this and theta of t is this, where theta phase is nothing but a function of time. Now if I pass it through a squarer circuit in the signal square technique, it will be is 0.5 square y plus cos 2. Now this is not cos 2 omega ct, it is cos 2 omega ct plus 2 theta. So phase, which is a function of time over here. So this is not a pure carrier frequency as required. So it's not a pure sinusoid. So it is not possible for SSB-SC. This you can see show it for the Costas loop too. So for the SSB-SC in general, we don't need also, because if you consider for the voice signal, then there is no problem whether it is a frequency error or a in the phase error, it results into phase distortion. But if it's a voice signal, that's not an issue. Okay, and frequency error generally there will be no problem. Okay, whatever be the case, whichever type of signal you have. Now, if you compare SSB signal and DSB-SC with reference to the bandwidth, then you know that for the DSB-SC, if the message signal is having a bandwidth of B hertz, then for the DSB-SC you require 2 B hertz, and for SSB-SC you require only B hertz. Now the effect of frequency and phase error during synchronous demodulation, if you take, then the effect is less on the SSB-SC compared to the DSB-SC. Now if you talk about the selective fading also, it is less in the DSB-SC because in the SSB-SC compared to DSB-SC, because in the SSB-SC there is only one sideband that is being transmitted. Okay, that's fine. In the case of the DSB-SC, 2 sidebands that have been transmitted. So selective fading is going to be the main problem in that. Only one problem in SSB-SC is that the generation of high level SSB signal is certain complicated, more difficult compared to the DSB-SC. It's not that simple as we think. It's ideal ideal pi by 2 shifter is not possible. Hider filter is not possible. It is slightly difficult, right? But point of view, if there is slightly difficult, but it works better compared to the all three. Okay, thank you. So all this presentation I have made it in the Microsoft Office license version. The books that I have referred for preparing this presentation for the lecture is by B.P. Lathi, Modern Digital Analog Communication, but in the second edition, not the third one, second edition. And the Communication System Engineering by John Prokis Salai, which is a well-known book, second edition. Its ISBN number is also available here. So if you want to check, you can check it in the libraries. Right? So thank you for time being. Okay, if you have any doubt, then you can contact me on this 2 email IDs, smith.ec@dd.ac or smith@alumni.iitd.ac. Hope it's. And now whatever content remaining for this part is related to the, so we have gone through frequency, effect of frequency and phase error. Now effect of interference and noise in AM system, that is what we left out in this portion. Okay, thank you very much.